Module 5, Lecture B, Sorted and Reversed. By the end of this lecture, you will be able to use sorted to order iterables with and without custom key functions and reverse flags, apply reversed to sequences, and understand when it can be used directly versus via slicing or other techniques, and combine sorted and reversed with collection constructors to produce ordered lists, tuples, or dictionaries. Sorted essentials. Natural ascending order. A basic sorting function arranges items in their natural ascending order. For numbers, it orders them from smallest to largest. And for text, it follows standard character rules, usually alphabetical order. This function returns a new, sorted list while leaving the original data unchanged. This is useful when you want to keep the original list intact, but also work with or display a sorted version. When you sort a set of values, such as exam scores or daily temperatures, you arrange them from the lowest to the highest. This makes it easy to identify the minimum and maximum, understand how the values are spread out, and notice any unusual outliers. In a similar way, sorting city names alphabetically creates an order that people expect, which is useful for indexes or menus. Overall, sorting helps organize data so it is easier to search, compare, and interpret. Natural ascending order depends on data types and language rules, which can affect how items are sorted. For simple data, like integers or lowercase words, the default order usually matches what we expect. When you mix uppercase and lowercase letters or use accented characters, sorting may follow character codes instead of an intuitive order. Default sorting often works for basic tasks, but as data becomes more complex or visible to users, you may need custom sorting to keep results clear and accurate. Python code, natural ascending order. We will explore how to arrange data in natural ascending order using the sorted function with both numbers and words. The key idea is that sorted creates a new ordered list while leaving the original data unchanged. By comparing how numbers are ordered from smallest to largest and how words are ordered alphabetically, we can clearly see the difference between numeric and text ordering. Simple classroom-style examples will make these behaviors easy to observe and understand. We begin with a list of exam scores, where each number represents a student's percentage on a test. The scores are stored in no particular order. This unordered list will later help us show how sorting functions can organize the data. Importantly, these functions can sort the scores without changing the original list itself. We begin with a list of city names that intentionally mixes uppercase and lowercase letters, such as Dallas, Atlanta, Chicago, Boston, and Austin. This list is used to show how sorting functions work when text data is not consistently capitalized. By examining how the sort order changes with this mixed case list, we can better understand how text sorting handles differences in letter case. We take the list of exam scores and use a sorting function to arrange them from the lowest value to the highest. The sorted results are saved in a new list called sorted scores. This process does not change the original list, so we can still access the unsorted scores and compare them with the ordered version later. We use the sorted function to arrange a list of city names in natural ascending order, meaning alphabetical order. This function takes the original list and produces a new list where the city names are sorted. The original list is not changed, so we can still refer back to it. This makes it easy to compare the unsorted and sorted versions if we need to. The code first displays the original list of exam scores to show the unsorted data as a starting point. It then displays a second list where the same scores have been arranged in ascending order using the sorted function. This illustrates that the sorted function produces a new, ordered list from lowest to highest, while leaving the original list unchanged. The comparison makes clear how the function organizes data without modifying the initial dataset. We first display the original list of city names so we can compare its initial order with the order after sorting. Then we show the list produced by the sorting function, which arranges the city names in ascending alphabetical order. This sorting respects case sensitivity, so names starting with uppercase letters come before those starting with lowercase letters. Overall, this demonstrates how the sorting function can reorder text data while leaving the original list unchanged. This script shows how sorting works in Python using the sorted function. It begins with unsorted exam scores and city names, then creates new lists where the scores are ordered from lowest to highest, and the city names are arranged in natural text order. The original lists are not changed, which demonstrates that the sorted function returns new ordered lists instead of modifying the existing data. It also highlights that sorting text is case sensitive, so names starting with uppercase letters come before those starting with lowercase letters. Period. Custom sort keys. Custom sort keys let you control how items are compared during sorting instead of relying on the default order. You do this by providing a function that pulls out a specific attribute from each item, such as a name, an ID, or a GPA in a student record. The sorting process then uses only that extracted value to decide the order. In this way, the key function acts like a lens that focuses the sort on exactly the attribute you care about, without changing the underlying data. When you use custom sort keys, you decide which aspect of your data to sort by, rather than changing how the data itself is compared. The data structure stays the same, but you choose a specific attribute to prioritize, such as price for budget decisions or stock level for inventory management. In data analysis, you might sort values by their absolute size to emphasize large deviations. The key function reduces each item to a single value that represents your sorting goal, and the sorting process then orders the data based on those values. Custom sort keys let you define special rules for ordering data that are hard to handle with direct comparisons. For instance, you can sort city names while ignoring case and spaces so that different versions of the same name are treated equally. You can also sort event times, stored as text, by using a key function that converts them into date and time objects first. By doing these transformations inside the key, your sorting code stays clear and better reflects how you actually want the data to be ordered. Python code. Custom sort keys. This section shows how to use the sorted function with simple, custom key functions. You will see how to sort a list of products first by price and then by stock level, without altering the original list. The key function controls which attribute is used for comparison. So, changing the key changes the ordering of the results. This demonstrates that sorted produces a new, differently ordered view of the same underlying data. We create a list of products where each product is stored as a small record with 3 pieces of information: its name, its price in dollars, and how many units are in stock. For example, the list includes a notebook, a pencil, a marker, and an eraser, each with its own price and stock quantity. Organizing the data this way makes it easy for the program to access and work with product information, such as when we want to sort items or perform other operations later in the code. We begin by printing a short message to explain that we are about to show the original list of products in its current order. Then, we loop through the list, and for each product, we display its name, its price in dollars, and how many units are in stock. By doing this for every item in sequence, we show all product details exactly in the order they appear in the list. This confirms that the list has not been changed at this stage. We sort a list of product dictionaries by price using a custom key. To do this, we call the sorting function with a small anonymous function that pulls out the price value from each product. The function returns a new sorted list without changing the original one. We then loop through the sorted products and print each name, price, and stock to show the new order based on price. We sort the list of products by their stock levels using a different sorting key. To do this, we call the sorting function with a small helper function that pulls out the stock units from each product dictionary. This creates a new list ordered by how many units are in stock. We then loop through this sorted list and print each product's name, price in dollars, and stock units to show the products arranged by stock level. This script shows how to sort a list of products using custom keys without changing the original data. It first displays the products in their initial order, including each name, price, and stock level. Then it creates a new ordering based on price by using a custom key that pulls out the price from each product, so the products appear from lowest to highest price. Next, it does the same with stock levels, using a custom key to sort from the lowest to the highest stock. Throughout, the original list stays the same, demonstrating that custom key sorting can produce new sorted views while preserving the original list. Sorting in reverse. To sort results in descending order, use the reverse option in your sorting function so the usual order is flipped and the largest values appear first. This is useful for tasks like ranking students by highest scores or listing products from most to least expensive. Using the built-in reverse feature is better than manually reversing a sorted list because it keeps your code clearer and more efficient while leaving the comparison logic unchanged. Using a reverse option together with a custom sort key lets you sort items based on a derived property, such as string length or order value, and choose whether the largest or smallest values come first. The key function defines what measurement you sort by, and the reverse setting controls the direction of that order. For example, you can sort research articles by citation count in descending order, so the most cited work appears first. This makes it easy to highlight the most important items according to a specific criterion in a clear and flexible way. When you need a descending sort, it is usually better to use the reverse option in the sorting operation instead of sorting in ascending order and then reversing the result. This makes your intent clear, improves readability, and reduces the chance of reversing the wrong sequence. It also avoids an extra processing step, which can matter for performance with large datasets. Consistently using the reverse flag leads to more efficient and professional code in software development and data analysis. Python code. Sorting in reverse. Demonstrate how using the reverse option in a sorting operation changes the order of items, and clearly contrast ascending order with descending order using simple numeric scores. Show that in ascending order, smaller scores come first, while in descending order, larger scores come first. Then illustrate how the reverse option can be combined with a key function so you can sort by a custom criterion while still getting the results in descending order. We begin with a list of numeric values that represent heights measured in inches. This list serves as the data we will use to demonstrate how sorting works. First, we display the list in its original order, so we can clearly see how the values are arranged before any sorting is applied. This initial view provides a basis for comparing the list before and after the sorting operations. We begin by sorting the list of height scores measured in inches so they are arranged from the smallest value to the largest. A sorting function is used to create a new list that contains the same scores, but now in ascending order. This new ordered list is then stored for later use. Finally, we display the sorted list so we can clearly see how the original unsorted scores have been rearranged into ascending order. To arrange the height scores from highest to lowest, we sort the list in descending order using a sorting function with the reverse option turned on. This option tells the function to order the values from largest to smallest instead of the default ascending order. After the sorting is complete, we display the updated list so we can see the scores in descending order. We define a list of student records where each record is a pair containing a student's name and score. This structure makes it easy to manage and organize the data, especially when we want to sort or filter by name or by score. In this example, the list includes Alice with 88, Bob with 95, Carlos with 78, and Dana with 92. Setting up the data this way prepares us for later operations that work with these scores and names. We begin by showing the original list of student score pairs to establish the starting order of the data. This initial display serves as a reference point before any sorting is done. By comparing the original list with the later sorted versions, we can clearly see how the order of the scores changes. We have a list of students, where each student is represented by a name and a score, and we want to sort this list by score. To do this in Python, we use the sorted function with a key function defined by a lambda expression that pulls out the score from each student tuple. We also set the reverse option to true so that the list is ordered from the highest score to the lowest. After sorting, we print the list to show the students arranged from top scores down to the lowest scores. This script shows how to sort data in Python in both ascending and descending order. It first works with a simple list of numeric scores, displaying the original list, then the list sorted from smallest to largest, and then from largest to smallest using a reverse option. It then moves to a list of students represented as name and score pairs, shows the original list of tuples and sorts them by the score value in descending order. This is done by combining the reverse option with a key function that pulls out the scored from each pair. Overall, the example highlights how the reverse setting and a key function can control sorting for both simple lists and lists of tuples. Custom sorting basics. Sorting dictionary items. When working with dictionaries that map labels to values, the default order of items is often not what you need. To sort them usefully, you decide which part of each key value pair should control the order, such as the price in a product list or the grade in a student list. You can think of each pair as a small record with two fields and define a rule that orders these records by one field or by some transformation of it. This shifts the problem from abstract dictionary sorting to sorting a sequence of two-part records, which matches how most programming tools are designed to work. To sort dictionary items, you first treat them as a sequence of key value pairs and then apply a sorting operation to those pairs. You choose whether the order is based on the keys or the values, depending on your goal. For example, you might sort countries by population to go from most to least populous, or sort expense categories alphabetically by their names. You can also transform the part you sort by, such as converting text to lowercase for case-insensitive ordering. After sorting the items of a dictionary, you can either keep them as a list of pairs for tasks like generating reports, or rebuild a dictionary so you can use the sorted order in later operations. Because modern dictionaries preserve the order in which items are inserted, reconstructing them from sorted items lets you iterate in that order, which is useful for exporting data or building menus. In data processing, sorting by things like timestamps or priority levels helps organize events or tasks. Overall, sorting gives structure to your data, making patterns easier to see and decisions easier to make. Python code, sorting dictionary items. This lesson explains how to sort the contents of a dictionary by either its keys or its values. You learn to use the sorted function together with the dictionary's items and an appropriate key function to control the sorting behavior. After sorting, you then build a new ordered dictionary from the sorted items so you can reuse this consistently ordered data later in your program. We create a dictionary that links fruit names to their prices in dollars. It contains 4 entries: apple, banana, cherry, and date, each with its own price. This structure lets us quickly look up the price of any of these fruits. It also makes it easy to use and update the price information in later steps of a program. We begin by sorting the dictionary entries by their keys, which represent the item names. Using the standard sorting function on the dictionary's items automatically orders them based on the first element in each key value pair. This produces a list of pairs where each pair contains an item name and its price. The list is arranged alphabetically according to the item names. To sort dictionary items by their prices, we use the sorted function on the dictionary's key value pairs. We provide a key function defined with a lambda expression that takes each pair and returns the price value. This tells the sorting process to order the items based on price instead of the item name. The result is a list of pairs arranged from the lowest price to the highest. We build a new dictionary that keeps the items in the same order they were sorted by price. To do this, we take the list of items that has already been sorted from cheapest to most expensive and convert it into a dictionary. Because Python dictionaries preserve the order in which items are inserted, the resulting dictionary reflects the price order established in the previous sorting step. We begin by displaying the original order of items in the dictionary by turning its items into a list, which lets us clearly see how they were first stored. This initial view of the sequence is important because it serves as a reference point. Later, when we apply different sorting methods, we can compare the new order to this original list. This comparison helps us understand exactly how each sorting operation changes the arrangement of the dictionary items. This line prints the dictionary items in alphabetical order based on their names. It relies on a list of items that was already sorted earlier. By displaying this sorted list, it presents the data in a clear, organized way and makes it easy to compare the original order with the order based on item names. This line displays the dictionary items ordered by their prices. Earlier, the items were sorted using a function that looks at the price in each item pair. The result is a list of item and price pairs arranged from the lowest price to the highest. When printed, you can clearly see the items listed in order of increasing cost. This line prints the contents of the ordered dictionary that was created to keep items sorted by price. By turning the dictionary items into a list before printing, it makes the output clearly show the preserved insertion order. As a result, you see the items listed from the cheapest to the most expensive, reflecting the original sorting by price. This script shows how to sort a dictionary by both its keys and its values. It starts with a dictionary that maps fruit names to their prices, then sorts the items alphabetically by fruit name using the default sort behavior. It also demonstrates sorting the same items by price using a custom rule that looks at the value in each pair. After sorting by price, it builds a new dictionary that preserves this sorted order. The output lets you compare the original items, the items sorted by name, the items sorted by price, and the final ordered dictionary, illustrating how to organize and display dictionary data in a structured way. Multi-field sorting. When you sort data by several fields, such as program, year, and grade point average, you are doing multi-field sorting, where each field has a priority. You might first group records by program, then sort within each program by year, and finally by grade point average within each year. Reversing the final list later, using a tool or slicing, does not change these comparison rules. It only flips the already sorted sequence. This distinction matters because it determines whether you need to change the sorting criteria themselves, or simply reverse the fully ordered results to match your intended outcome. Multi-field sorting works like a chain of tiebreakers. The first field, such as department, sets the main order. And if two items match there, the next field, like course level, decides between them, followed by a third field if needed. Changing the sort direction simply reverses the final list without changing which fields break ties or how they are applied. This lets you keep consistent sorting rules while viewing the same data in either ascending or descending order. In areas like human resources and logistics, it is common to sort records by several fields so the data stays organized and meaningful. For example, employees might be ordered first by department, then by job title, and then by hire date, so that more experienced staff appear before newer hires within each role. Shipments can be arranged in a similar way by region, priority, and delivery date. After creating this multi-field order, you can reverse the sequence to change the viewing direction, such as showing the most recent hires first, while still preserving the original sorting priorities. This makes data views both predictable and flexible for analysis. Python code. Multi-field sorting. Use a simple set of student records to demonstrate how to sort by multiple fields at once. You can give the sorting function a key that returns a tuple, such as first, the last name, and then the first name, so it compares the first field and only uses the second when needed. This shows how multiple keys work together to control the order. Finally, reversing the sorted sequence flips the overall direction of the results, while keeping the same priority of fields in the sort. We create a list called students that holds several tuples, where each tuple is one student's record. Each record stores 3 pieces of information: the student's program, their year, and their grade point average. For instance, one record might describe a physics student in their second year with a grade point average of 3.4. Organizing the data this way makes it easy to manage and sort students based on program, year, or grade point average. We begin by printing a message to show that we are about to display the student records in their original order. Then we go through each student record in the list one by one. For each record, we print it so that all the student details appear exactly as they are stored in the original list. We sort the list of student records, first by program, then by year, and finally by grade point average in descending order. To do this, we use a sorting function with a key that returns a tuple containing the program, the year, and the negative of the grade point average. Using the negative value makes higher grade point averages come first, while the program and year remain in normal ascending order. After sorting, we go through the reordered list and print each student record to show the new arrangement. We first print a message to indicate that we are about to show the student records in reverse order. Then, we create a new list by taking the already sorted student records and applying the reverse operation, which produces the same records but in the opposite sequence. We convert this reversed sequence into a list, and finally loop through it to print each record. The result is that we see the students displayed in the reverse of the original sorted order, while still respecting the same sorting criteria. This script works with a list of student records and demonstrates how to sort them using multiple fields. Each student is represented by their program, year, and grade point average. The records are first displayed in their original order, then sorted mainly by program, then by year, and finally by grade point average in descending order by using a key that reverses the grade values. After showing this sorted list, the script reverses the order of the sorted records and prints them again to illustrate how reversing changes the sequence while keeping the same sorting priorities. Sorting custom objects. When sorting custom objects like student records, products, or books, you must decide which attributes control their order. For example, you might sort books by year, rating, or title, depending on your goal. Because these objects do not have a built-in order, you define what counts as coming before or after based on your needs. After sorting, you can also reverse the order to see the highest values first, or to focus on the most recent or most important items. When working with custom objects, it helps to separate how they are stored from how they are ordered. For example, you might sort job applications by assessment scores to group the strongest candidates, then reverse the sorted list to focus on lower scoring ones without changing the objects themselves. This same idea applies to any ordered data, such as medical records or sensor readings, as long as you have already sorted them by your chosen criteria. In short, once data is ordered, you can freely reverse that order without worrying about its internal structure. Reversing sequences of custom objects lets you view the same data from different angles without changing how items are compared. For example, in logistics, you might sort shipments by departure time to see the earliest first, then reverse the order to focus on the latest. In finance, you can sort transactions by amount and reverse the sequence to switch between large and small expenditures. Overall, sorting structures your data, and reversing it provides a quick way to change perspective for flexible analysis. Python code, sorting custom objects. This section explains how to sort custom objects based on their attributes and then reverse the order of the results. It shows that the sorted function can easily create ordered lists of these objects when you specify which attribute to use. It also demonstrates that the reversed function can then walk through the sorted custom objects in the opposite direction, allowing you to process them from last to first. We define a shipment class to represent each shipment with key details. Its constructor method runs whenever a new shipment is created and takes three inputs: the destination, the weight in pounds, and the departure hour. These inputs are stored as instance variables, so each shipment object keeps track of its own destination, weight, and departure time. This structure makes it easier to manage and later organize shipments based on these attributes. This method controls how a shipment object is turned into a readable string. When you print a shipment, it shows the destination, the weight in pounds, and the departure hour in a clear format. This makes it easier to see the current state of the object, which is especially helpful for debugging and logging. We create a list of shipment objects, where each shipment represents a delivery with certain attributes. One shipment is for New York with a weight of 120 pounds and a departure time of 9. Another is for Chicago with a weight of 80 pounds and a departure time of 7. The last shipment is for Dallas, weighing 200 pounds and departing at 11. This list will later be used to show how to sort and reverse shipments based on their attributes. We have a list of shipment objects, and we want to order them by their departure hour. To do this, we use a sorting function that takes the list and a key parameter. The key is a small function that pulls out the departure hour from each shipment. The result is a new list where the shipments are arranged in ascending order of their departure time. We begin by announcing that the shipments will be sorted by their departure time in ascending order, so the listener knows how the results are organized. Then we display the list of shipments after sorting, which reveals the sequence from the earliest departing shipment to the latest. This allows the user to clearly see which shipment leaves first and how the others follow in order. To view the shipments in reverse order, we first take the already sorted list and apply a reversing operation that walks through it from the end back to the beginning. This operation initially produces an iterator, which is a tool that lets us step through the items one by one. We then convert this iterator into a regular list so it is easier to handle and display. The result is a new list of shipments ordered from the latest to the earliest departure time, which is the opposite of the original sorted order. We first add a blank line and a short message to signal that we are now showing shipments in reverse order, emphasizing the most recent departures. Then we display the shipment list that has been reversed from its previously sorted order. This reordered list starts with the latest departure times and moves backward, giving a different view of the same shipment data. This script works with a list of shipment objects, each with a destination, a weight in pounds, and a departure hour. It first sorts the shipments by departure time in ascending order, so they appear from the earliest to the latest departure. Then, it reverses that sorted list to show the shipments from the latest departure back to the earliest. Overall, it demonstrates how to sort and reverse lists of custom objects in Python to change the order in which they are viewed. Working with reversed. Using reversed with sequences. When working with sequences, such as lists, tuples, or strings, you may need to access elements in reverse order. The reversed function lets you do this by creating an iterator that goes from the last element to the first without changing the original sequence. This is useful when you want to process items from most recent to oldest, like reviewing log entries or checking a string backward, while still keeping the original order available. In this way, reversed provides a clear and efficient way to work with a reversed view of your data. The reversed function produces an iterator rather than a new collection, which makes it useful for building different reversed data structures. When you pass this iterator into a list constructor, you get a new list with the elements in reverse order, and using a tuple constructor gives you a reversed tuple for an immutable snapshot. You can also reverse strings by joining the characters from this iterator. Overall, reversed controls the order, and the constructor you use determines the type of collection you create. You can think of the reversed function as a way to create a new collection from an existing sequence without changing the original data. For example, you might reverse a list of events to start from the most recent and store that result as a new list or tuple for reporting. You could also reverse a project plan's milestones to highlight upcoming tasks and save that view as a separate tuple. Keeping these reversed versions separate from the original data makes your transformations clearer and your programs easier to read and maintain. Python code using reversed with sequences. This section focuses on using the reversed operation with simple sequences and constructors. It shows how to apply reversed to lists, tuples, and strings to obtain new collections in reverse order. The key idea is that the original sequences remain unchanged while reversed versions are created. This helps you understand how to work with reversed views of data without modifying the original structures. We create a list of daily temperature readings measured in Fahrenheit, where each value represents the temperature for one day. Storing these numbers together in a list makes it easy to work with them as a group. For example, we can later reverse their order or use them to calculate averages and perform other simple analyses. The reversed function creates an iterator that lets us go through the list of temperatures, starting from the most recent value and moving back to the earliest. It does not change the original list. Instead, it simply provides a way to access the same elements in the opposite order. We create a new list by using an iterator that goes through the original list of temperatures in reverse. Passing this reversed iterator into the list constructor builds a separate list with the temperatures in the opposite order. The original list is not changed, so we get a reversed snapshot of the data. This lets us work with the temperatures in a different sequence without modifying the initial dataset. We define a tuple called route cities that holds a sequence of city names in the order they will be visited. This tuple represents a fixed travel route, so the order of cities is preserved. Because tuples are immutable, the route cannot be changed once it is created. This is useful when the travel path must stay consistent and unaltered throughout the program. To reverse the order of cities stored in a route tuple, you first apply the reversed function, which creates an iterator that moves through the cities from last to first. You then pass this iterator into the tuple constructor to build a new tuple. The result is a separate tuple that contains the same cities but in reverse travel order, giving you a fixed snapshot of the reversed route. This example shows how to reverse a string in Python. We start with a string that contains the word hello. The reversed function is used to create an iterator that goes through the characters in reverse order. Then, the join method combines these reversed characters using an empty separator to form a new string. The result is a reversed version of the original word, demonstrating how built-in functions can be used to reverse a string. To reverse the characters in a string, you can apply a function that reads the characters from the end back to the beginning. This function produces a sequence of characters in reverse order. You then use a method that joins these characters together into a single new string. The result is a reversed version of the original message, which you store for later use. We begin by printing the original list of temperatures in Fahrenheit to show its initial state. This makes it clear that when we later reverse the list, the original data itself is not changed. By comparing the original and reversed versions, we can see the effect of the reversal operation while confirming that the starting list remains intact. This line prints the list of temperatures in reverse order. It uses a list that was already created from a reversed version of the original sequence. This shows how you can reverse the data and store it in a new list, so you can view the temperatures backwards without changing the original list. We begin by printing the original tuple of city names, which represents a planned travel route. This shows the cities in their initial sequence. Having this original order visible makes it easy to compare with the reversed version later. By contrasting the two, we can clearly see how the order of cities changes when the tuple is reversed. This line outputs the tuple of city names in reverse order, representing traveling backward along the route. The reversed version was created earlier by using a function that walks through the original tuple from the end to the beginning. A new tuple was then built from this reversed sequence. This shows how you can reverse the order of elements while leaving the original tuple unchanged. We begin by displaying the original message stored in the message variable so we can see the exact sequence of characters before any changes are made. Showing this initial string is important because it provides a clear reference point. Later, when we look at the reversed version, we can directly compare it to the original and clearly see the effect of the reversal process. We display the message string in reversed form to show how its characters have been transformed. This is done by using a reversing function together with a method that joins the characters back into a single string. The printed result confirms that the sequence has been reversed, while the original string remains unchanged. This script shows how to reverse different types of sequences in Python using the reversed function. It first reverses a list of temperatures in Fahrenheit to create a new list while keeping the original list unchanged. It then reverses a tuple of city names to represent a travel route in reverse order. Finally, it reverses a string by joining characters from a reversed sequence, demonstrating how to reverse text. In each case, the output displays both the original and the reversed version, emphasizing that the original data is preserved and only new reversed versions are created. Safe reverse iteration. Safe reverse iteration means looping through data from the end to the beginning while keeping the original structure unchanged. When you iterate forward and modify the data at the same time, you can accidentally skip elements or cause errors because the collection is changing as you traverse it. Simply reversing the direction of the loop does not fix this problem. Instead, you should use a stable representation, such as a reversed view or a copy of the data, so you can filter or transform elements without disrupting the order of iteration. The key idea is to maintain data stability throughout the loop. When you need to remove or insert elements while scanning a collection, it is safer to iterate over it in reverse. If you move forward and remove items, the shifting positions can cause you to skip or mishandle elements, such as notifications you want to cancel. By using a stable reversed view, you keep the structure of the collection unchanged while you decide what to keep or discard. This makes it easier to see which elements have already been processed and ensures that any new list, tuple, or dictionary you build from the results has a clear, predictable order. When you use reverse iteration to build new collections, it is important to keep the original data unchanged. This is especially true for things like financial transactions or reversed key-value pairs, where the order needs to reflect the real state of the data for interfaces or analytics. Treat reverse iteration as a read-only process and apply any modifications separately. This keeps your collections consistent, meaningful, and easier to understand. Python code. Safe reverse iteration. First, show how removing reminders from a list while iterating forward over it is unsafe, because changing the list as you move ahead can cause items to be skipped or processed incorrectly. Then contrast this with a safe approach that iterates in reverse, using a reversed view of the list together with creating a new list. Emphasize that this reverse iteration keeps the final list order predictable and easy to reason about. Since you control exactly which items are removed and how the resulting list is constructed. We begin with a list of reminders that hold several text items, such as tasks like paying rent or calling mom. Some items in the list start with the word old, like an old bill or an old coupon, and these are intended to be removed later. This setup illustrates how Python lists can store multiple pieces of information and how you can later filter out certain entries based on a condition. Overall, it provides a simple example of managing and cleaning up list data in a program. We begin by showing the reminders list in its original order so we have a clear reference before making any changes. This initial display lets us see the starting state of the data. By comparing later modifications to this original view, we can better understand how the list has been altered. This example demonstrates unsafe behavior when removing items from a list while looping over it. We first copy the original reminders list so the original stays unchanged, then iterate through the copy. During the loop, if an item begins with the word old, we remove it from the list. Because we are changing the list's length as we iterate, this can cause unexpected results. Finally, we print the modified list to show the outcome of this unsafe removal approach. This example demonstrates a safe way to remove unwanted items while iterating over a list. We first copy the original reminders list so it stays unchanged. Then create an empty list to hold the items we want to keep. Using a reverse view of the copied list, we check each item and keep only those that do not start with the word old. By working on a copy and collecting the desired items separately, we avoid modifying the list we are currently iterating over. We take the list of items that were kept and reverse it so we can restore their original order after filtering. Using a reversing operation creates a reversed view of this list, which we then convert back into a regular list to make the final order clear and predictable. When we print this final list, it shows all the reminders that did not start with the word old, now arranged in the same order they had before any filtering was done. This script compares unsafe and safe ways to remove items from a list while iterating over it. First, it shows that trying to delete reminders that start with the word old while moving forward through the list can cause some of those items to be skipped because changing the list during iteration leads to unpredictable behavior. Then it demonstrates the safer method. It iterates through the list in reverse, builds a new list with only the items that do not start with old, and finally, reverses that new list to restore the original order. This approach reliably filters the list while keeping the remaining items in the correct sequence. Lists and tuples. Reverse iteration combined with list or tuple construction lets you create new reversed sequences without altering the originals. You can treat the reversed view as a temporary way to walk through the data from end to start. Then pass it into a list constructor to get a separate list in reverse order. This is useful when you need a reversed version, such as for a chronological log, but must preserve the original sequence. The same idea works for tuples, giving you an immutable, reversed snapshot that can capture final states or PABs for later review. Lists and tuples handle reverse iteration differently because lists are mutable and tuples are not. With a list, you can either reverse it in place or create a separate reversed list, which is safer when the original list is shared by different parts of a system. For instance, one component can work with its own reversed copy without changing the list used elsewhere. Tuples, however, cannot be changed, so reversing them always means creating a new tuple. This is useful when you want a reversed view of a sequence of steps or checkpoints while keeping the original order intact. By combining reverse iteration with filtering and collection constructors, you can build new ordered collections that match your needs. You might start with a list, filter its elements, then reverse the order and choose whether to store the result in a list or a tuple, depending on whether you want it to be changeable. In data analysis, this helps you create a reversed tuple of selected days that stays fixed. In user interfaces, it lets you reverse a list of actions to show the most recent ones first without changing the original data, making your code's intent and control over mutability clearer. Python code, lists, and tuples. To reverse sequences without changing the originals, create new reversed versions instead of modifying them in place. For lists, use a reversed view together with a list constructor to build a new list in reverse order. For tuples, use the same reversed view with a tuple constructor so the result stays immutable. Then, compare the original sequence with its new reversed version to clearly see that the original data has not been altered. We define an events list that records a sequence of user actions in the order they occur. In this example, the events are login, view page, add to cart, and checkout. This ordered list acts as a simple timeline of actions. We will use it later to show how to work with and manipulate lists. To create a reversed copy of a list of events without changing the original, you can use a function that returns a view of the list in reverse order. This reversed view is then given to the list constructor, which builds a new list from it. As a result, the original list stays the same, and you get a separate list that contains the events in the opposite order. We first display the original list of events to confirm its current order and show that it has not been modified. Then, we display a reversed version of this list, which is created as a new list using the reversed view. This demonstrates that reversing the list in this way produces a separate list and does not change the original data. We define a tuple called the configuration steps tuple, which holds a fixed sequence of actions that must run in a specific order. These actions include starting the server, loading the configuration, running checks, and then accepting requests. Using a tuple guarantees that this order cannot be changed, which helps protect the integrity and reliability of the configuration process. To reverse a tuple, you can use a reversed view that gives you the elements in reverse order. Then pass that reversed sequence into the tuple constructor to build a new tuple. This process does not change the original tuple. Instead, it creates a completely new one with the elements in reverse, which preserves the immutability of tuples. We first print the original tuple of configuration steps to show that it stays the same, which illustrates that tuples are immutable and their order cannot be changed. Then, we print a reversed version of this tuple, which is a new tuple with the elements in the opposite order. Comparing these two outputs shows that we can create new sequences, such as a reverse tuple, without modifying the original one. This highlights both the immutability of tuples and how new ordered collections can be derived from them. This script shows how to reverse sequences in Python without changing the originals. It starts with a list of event names and creates a reversed copy using the built-in reversing tool together with a list constructor, leaving the original list unchanged. It then does the same with a tuple of configuration steps, using the reversing tool and a tuple constructor, so the original tuple also stays intact. When you run the code, it prints both the original and reversed versions, demonstrating how to work with reversed sequences while preserving immutability. In this lecture, you learn to use sorted to order arrables with and without custom key functions and reverse flags, apply reversed to sequences, and understand when it can be used directly versus via slicing or other techniques, and combine sorted and reversed with collection constructors to produce ordered lists, tuples, or dictionaries. In the next module, Module 6, we will go over introspection and metadata. Thank you for your attention. See you all in the next lecture.